We've talked about evaporation and condensation. Now we're going to talk about a different state change between a solid and a liquid. So melting, freezing, and sublimation. As you increase the temperature of a solid, the thermal energy increases. The particles, the molecules, increase in their kinetic energy, and they vibrate faster. They're held together by these intermolecular forces. When that vibration gets strong enough, it causes some of those intermolecular forces to be broken and allows the particles to slide around near each other. And so that's melting. And so we get a liquid. So at that point, that's called the melting point, and that's where the kinetic energy of the particles is able to overcome the intermolecular forces that are holding them together. So let's see. When ice melts, the water molecules are breaking free. So that's like, in the classroom, it's like the students are getting agitated and they get up out of their seats and they mill about, and that's a liquid. What's interesting is just like with the boiling, as long as the ice and water are both present, if you have both states present, the temperature will be 0 degrees Celsius. So an ice-water mixture, provided, it's pure ice and water at atmospheric pressure, is going to have a temperature of 0 degrees Celsius. So this is at 0 degrees Celsius. It doesn't matter if there's a little bit of ice, a lot of ice, the temperature here, where they're both present, is going to be the same. Just like when we boiled the water, we talked about boiling, the temperature didn't rise. The temperature only rises after all the ice has melted. Because what's happening? What's happening here? Even if you're heating this, so if we're putting heat into this, that energy is going into increasing the temperature of the ice. Okay, so you increase the kinetic energy of the ice molecules, which causes them to break into the liquid. Okay, so the energy, the heat energy that's being put in is being used to break those intermolecular forces, and the temperature is not rising yet. So the molecules are moving away from each other, but they're not moving any faster. It's a little hard to explain this early in the morning. Yes?
When you graph the cooling, is it similar to boiling? To once the whole thing becomes ice, the temperature drops rapidly?
Yeah. In fact, here's the picture.
Oh.
Yeah, so you're good at predicting at least the future of lectures. So here is a heating curve looking at melting. So here we've got ice at minus 20 degrees Celsius, and as we add heat, the temperature of the ice increases. And when it gets to 0 degrees Celsius, then melting begins. And again, like with the boiling, the temperature remains flat. You're adding heat, but all you're doing is you're melting ice. You're not increasing the temperature. So you're melting the ice, and then once all the ice is melted, then the temperature of the water will increase. If you keep going, you'll get to the boiling point and you'll have another flat place. Okay, so the temperature will stay at 0 degrees until all of the solid is melted. So let's talk about energy, endothermic, exothermic. So to melt an ice cube, are you putting energy into it or taking energy out of it?
Putting energy into it?
Putting energy in to melt the ice cube, because you would want to heat it up. So melting is an endothermic process. That makes some intuitive sense. The reverse is true, that freezing something is an exothermic process, and that's a little harder to understand. But if you think of it as just being the opposite, then you can remember it. So freezing is exothermic. When something freezes, heat is released. So that doesn't generally happen spontaneously, does it? But what's going on in your freezer? How does your freezer work to make ice cubes? Well, the refrigerator does this too, it just doesn't go to as low a temperature. Your refrigerator freezer is pumping heat out of the inside of the freezer. It's removing heat. And you remove heat from something, the temperature goes down, and it goes down until it gets to the freezing point, and it'll stay there until it freezes. Where does that energy go that it's pumping out?
Behind the refrigerator?
It goes behind the refrigerator, right? And mine has a little fan, and there's this little warm air current coming out underneath. So if you ever have wet shoes, you know, like my kids, the boys only have one pair of sneakers because that's all they wear anyway. But occasionally, you know, they get really wet and muddy, and so you have to put it through the washing machine. Then what do? You've got wet shoes. You pull their tongues open, and you lay them on their side in front of the refrigerator, and by morning, they're dry. Because here you have this nice, dry, slightly warm air. It doesn't damage the shoes like putting them in the dryer. But you have this nice air coming through. And that's why you can't, you know, if you're hot and your air conditioner's broken, like ours was this summer, you can't just leave the refrigerator door open and expect it to cool off the kitchen, okay? Because yes, it's cooling the inside, but it's actually generating more heat on the outside than it's removing on the inside. It's a little bit like having your heater hooked up backwards, or your air conditioner hooked up backwards would be heating your house and putting cold air outside. That's kind of what a heat pump does. It separates warm from cold. Okay, so there's one more thing I want to talk about with that. And I don't remember, did I talk to you about this? I don't think I did. See, I do the same thing with the Reedley people, and then I can't remember who I talked to about this. So watering orange trees when it's freezing, did we talk about that? Yes, we did.
Yeah,
Okay, so you apparently weren't understanding that or didn't remember that. But that's okay, because I didn't remember either. So watering orange trees, because when the temperature gets too low, the oranges are going to freeze. And they water them, make sure the field is good and wet, because as water freezes, it releases energy. And the temperature will not drop below zero near that water until all of the water has frozen into ice. So as long as you've got some standing water in your field, you can help moderate the temperature. So there's the short version, since you apparently missed it on Tuesday. It's okay.
Come back to me.
Good.
Totally remember.
Yeah. So we talked about heat of vaporization, heat of fusion. So this is the energy required to melt 1 mole of a solid. And wow, that's the wrong equation. Did they get the right one over here? Yeah, okay. They've got these 2 equations backwards. This is the equation. Okay, I'll just fix it because I can. Good grief. I obviously didn't look at this very carefully.
That should be a plus.
This is the solid, and this is the liquid, and this is plus. There we go. Heat of fusion is melting. Now, fusion is not a word that you necessarily associate with melting. But what happens when you put a whole bunch of chocolate chips in a pan and you warm them up a little bit?
Fusion.
They fuse together into one big lump of chocolate, right? They're melting. Melting and fusing are the same thing. So fusion is heat of melting. The amount of heat required to melt 1 mole of a solid. And so we write the equation as the solid going to the liquid, not the other way around. And then that heat of fusion is positive because melting is endothermic. The energy has to go in. I don't know how
Is 6.02 like due to avocados? Or is that just
No, that's a coincidence. That's just one of those weird random coincidences. So this is the other way around, and this is a negative sign. I can do better than that. We could do this. It's like magic. There we go, minus. So make those corrections if you printed out these slides. So if we're freezing water, the energy is being given off, or being pulled out of it is probably easier to think of. And so delta H is negative because freezing is an exothermic process.
What does H represent? Energy?
Yes. Heat energy. So delta H means the change in energy because of that reaction. So for water, the heat of fusion is 6.02 kilojoules per mole. If you're freezing it, you have to take that much out. If you're melting it, you have to put that much in for every mole of water. And for other substances, it's going to be different. So let's see. We can use the heat of fusion to calculate the amount of energy needed to melt a given amount of a solid, or to, we can also use it if we're given the moles of a solid, and, no, if we're given the energy, sorry. If we're given the energy, we can calculate how many moles. So it's a conversion factor. It's kilojoules per mole. Let's write that down. That'll make me feel better. So not a good color. Kilojoules per mole. So that allows you to convert between energy units and moles of a substance. You can go back and forth either way. So I think we have an example here. Yes, we do. Calculate the amount of heat absorbed when a 15.5 gram ice cube melts at 0 degrees Celsius. They're telling us 0 degrees Celsius because the heat of fusion is generally expressed at that substance's melting point. So 15 grams, we have 15.5 grams of ice, and what do we want to find? We want to find the amount of heat. There's really no equation to memorize for this. We just use dimensional analysis. So we've got a mass of water, and we want to know heat. So that's going to be joules, kilojoules, something like that. We can't go directly here. We need to stop at moles, because the heat of fusion is in kilojoules per mole. On the previous slide, we learned that the heat of fusion, the delta H FUS, heat of fusion. Oh, let's try that one more time. I think my iPad's not happy about all the stickiness on the screen. There's like this film of child goo on it. Equals 6.02 kilojoules per mole. So heat of fusion, fusion is melting. And so melting is an endothermic process. This is a positive.
Is that specifically water, or is that for?
That's specifically for water. Good question. Other substances, it's a different number. So we can convert from grams to moles, right? That should be old hat. And this heat of fusion is what we're going to use for the moles to kilojoules. Molar mass is what we use in here. So 15.5 grams of water, and we need to convert to moles of water and then to kilojoules. So we get all of our units in here first. We decided we're going to go grams to moles to kilojoules, so we need to divide by moles here, so those cancel out, and divide by grams, so those cancel out. We need the molar mass of water. Well, it's 2 times 1.008 plus 16, which is 18.02 grams per mole. So this is 1 mole for every 18.02 grams of water. And then the heat of fusion was 6.02 kilojoules. So let's see the numbers here. 15.5 divided by 18.02 times 6.02. And we should round this to 3 sig figs, and I get 5.18. So this equals 5.18 kilojoules. So if you want to melt a 15.5 gram ice cube, you need 15.18 kilojoules of energy to do that. This just doesn't sound super practical, does it? But there are many situations, like if you're designing a car or doing various industrial processes where these sorts of calculations can be important. Any questions? So heat of fusion, heat of vaporization are both conversion factors relating amount of energy to the number of moles of that substance. No questions? Yes?
So the freezing point and the melting point of water is both 0 degrees?
Yes. Freezing point and melting point is the same temperature. It's just the idea of which direction are you going. If you're starting from the liquid, then you call it a freezing point. If you're starting with the solid, then you call it a melting point.
So at 0 degrees, water can be in 2 different states?
Mm-hmm. Yep.
Conceptually, it's weird. Like if you had
Well,
two-
yeah,
like
because
given
at
here-
0, you could have like pretty much all water or all ice. But it's not going to, I mean, if you leave it there, it's not going to stay. It depends on whether you're removing heat or putting heat in. Here is a heating curve for the whole temperature range from minus 25 to plus 125 degrees Celsius. So, wrong, I poked the wrong place. Okay, so down here, we're heating water. And what this is, it's a diagram showing a heating curve for ice. And it says correlate sections I, and I. I don't know, why couldn't it be A, B, and C? With the correct states of water. So let's do that and make sure we understand what this heating curve means. So here, this section right here, designated with a lowercase I, what state of water, what's the state of water there? It's melting, right? So at I, we have solid and liquid. Okay, here we just have solid. And so this one, what state of liquid do we have?
Liquid.
Sorry. Yeah, that was good. What state of liquid? Oh, it's liquid, she said it. Okay, and then what happens up here?
Boiling.
We have boiling, and so we have liquid present and we have gas present. And then up here, this part, what's that?
All gas.
That's all gas. I can't spell.
Is the slope of the solid and the gas the same slope, or is it just
No, it's a little different. The slope of that line is related to the specific heat capacity. So some things, if you give them X amount of energy, the temperature changes a little bit. Other things, it changes a lot. Metals heat up very quickly, water heats up very slowly. And so that has to do with the specific heat capacity, those slopes. Any questions? Okay, sublimation. So sublimation is also a physical change, but it's when something goes from the solid state directly to the gas state without melting. And you're like, how does that work? How's that possible? Well, it happens. I think you've probably all seen dry ice, right? So, actually, let's look at this picture. Here's a picture of dry ice. And the reason it's called dry ice is because it doesn't melt. Carbon dioxide does not melt. You cannot have liquid carbon dioxide at room temperature. It just doesn't melt. So what it does is it goes from a solid directly to a liquid, and you can see evidence of the gas down here, and that's probably, the color here is probably from it causing water molecules in the gas state to condense because it's cold. Carbon dioxide itself is colorless, but we see kind of a vapor trail here because of this cold gas that's coming down here. But it goes directly from a solid to a liquid. I'm sorry, solid to a gas. I'm trying to emphasize solid to gas. And so if you pack a cooler or a packing box and you mail it and it's got dry ice in it, as the dry ice sublimes, it doesn't get everything all wet. Okay, that's the problem with regular ice. You end up with this wet mess, right? So use dry ice in a cooler and nothing gets wet. So that can be a good thing. But it's also giving off a gas that builds up pressure. You've probably heard recently about carbon dioxide bombs. They're dangerous. And so you don't want to keep dry ice in a sealed container because the pressure will build up. My husband, when he was a kid, his mother was a pharmacist, and so they would get shipments of drugs that needed to be refrigerated, and they come with dry ice, and so she'd sometimes bring the dry ice home and let the kids play with it, because this was a different era when people did stuff like that. And he also had access to one of those giant pickle jars. Not just the big pickle jar like you might buy at Costco, one of these really big pharmacy pickle jars. And so he thought, well, what would happen if I put the dry ice in the pickle jar and put the lid on it? And he set it out in the middle of the backyard, and then he's sitting there waiting to see what will happen. And then he realizes, this is probably not a very good idea. There's a lot of pressure building up in this glass jar, and this could get ugly. So he got his BB gun, and he laid down on the far side of the yard, and he shot the jar with the BB gun. Yeah. Well, I think he's just, accelerating the inevitable. He realizes this is going to happen, and maybe let's just make this happen before Mom comes home. So the pickle jar exploded. He says it exploded so thoroughly that there wasn't even glass all over the yard. It just, broke into sand, basically. The lid, I don't know where the lid went, but there was this really large noise. His uncle comes running over because he lives next door. He opens the gate and he looks in. He understands what has happened and he mutters, "Stupid kids." And he goes away, because that's the sort of thing that happened when we were young. It was a better time. It was a very dangerous time. But that's the fun experience, the fun story I have about dry ice. But seriously, do not try this at home, okay? Because you could get in trouble with law enforcement. I mean, you could get hurt, but you can get in serious trouble. People do not think things like this are funny anymore. So dry ice is really fun, but not in a confined container. So it doesn't melt. It just doesn't. Even at minus 78 degrees Celsius, which is really cold, molecules on the surface of the carbon dioxide have enough energy to move directly into the gas state. So are the intermolecular forces that are holding those molecules together very strong? They can't be very strong if it's going to melt at minus 78 degrees. So there's the picture. Now, other things sublime too, but not so dramatically. Regular ice also sublimes. I don't know if you've ever had some really old ice cubes in your freezer. Maybe got lost in the back or something, and they're smaller than they were to start with. And what happened to them? Where did the ice cube go? I mean, it's in the freezer. It's frozen. What's it doing? Well, the ice will slowly sublime, and so your ice cubes will get smaller. And this happens in cold climates. I grew up in Minnesota, And the snow will slowly disappear on its own, even if it doesn't melt from the sun hitting it, because it sublimes. It goes directly from the frozen solid state into the gas state. I think there's another one about this. Yeah, and so you've heard of freezer burn on your food, and sometimes food that's been in there a long time gets kind of dried out and yucky, and you're like, what happened to this? Or you open a bag of tater tots, and it's got a whole bunch of ice crystals on the bottom. It's like, why'd they throw ice crystals into the bag of tater tots? Well, the water that was originally inside the food, you know, those tater tots made out of potatoes, they've got water in them. In the freezer, the water slowly sublimes out of the tater tots. They're in a bag, you can't go anywhere. So what does it do? Well, it eventually condenses somewhere else and freezes, and so you end up with this collection of ice crystals over here and your dried out tater tots over there. So how do you avoid that? Well, you can use like these food saver bags, or where you squeeze all the air out, because the less air there is around the food, the less space there is for the sublimation to occur. If there's really no space for the water molecules to sublime into, then they won't. The other thing that can happen, the other thing that helps is keeping your freezer extra cold. So the colder the temperature, the less sublimation there will be. And so that's why, you know, some people pay extra for these deep freezes, where it keeps them colder than regular freezers.